Okay, imagine trying to teach a computer language. It's already tough.
Uh-huh.
But then add translation, like hello becomes bonjour. Easy.
Right.
But what if you give it, I don't know, a huge paragraph, 50 words maybe, and the French version is 60 words long? How does a computer handle that? Inputs, outputs, different lengths. That was a real sticking point for a long time.
Absolutely. I mean, think about the dominant models back then. Your deep neural networks, DNNs, they were great, but for stuff with fixed sizes.
Like images, right, or audio snippets mapping to sound.
Exactly. Fixed inputs, fixed outputs. They sort of needed everything to fit neatly in the same size box every time.
So trying to translate a tiny sentence and then a massive one, with the same model expecting the same dimensions, it didn't really work.
Yeah, that fixed structure was a real limitation for sequence tasks. Translation, question answering, anything where lengths vary.
And that brings us right to the paper we're diving into today.
Yeah.
It tackled this exact problem.
It did. We're looking at sequence-to-sequence learning with neural networks, Sutskever, Vinyals, and Lego, Google. Foundational stuff.
Okay, so our mission here, let's unpack their approach. It sounds, well, surprisingly simple in concept. We want to see how they tested it and get into the results. Some are pretty unexpected.
Yeah, and the headline up front is, they built this, like, relatively straightforward neural network, and it actually beat the standard complex translation systems of the day.
Purely neural.
Purely neural. On a big benchmark task, it was a huge moment, really shifted things.
All right, so let's get into it. The core idea. It revolves around LSTMs, right? Long short-term memory networks.
That's right. Instead of forcing variable lengths into fixed slots, they used LSTMs in this kind of two-part system, end-to-end.
Okay, two parts. Tell me about them.
So first, you've got an encoder LSTM. Its job is just to read the input sequence, word by word.
Whole thing.
The whole input sentence, yeah. And as it reads, it sort of digests it, processes it, and boils it all down into one single fixed-size vector.
Like a summary. A numerical summary holding the sentence's meaning.
Exactly like that. Capturing the essence, you could say. Then the second part, the decoder LSTM, it takes that vector, that summary, and uses it as a starting point to generate the output sequence. So the translation, in their case. Again, word by word.
And LSTMs are good for this because,
Right.
well, they have that memory part, right? They can link things across long distances in the sequence.
Precisely. Language depends on that. A word way back at the start can affect a word much later. LSTMs are designed to handle those long-range dependencies.
Makes sense. Okay, so this encoder-decoder setup sounds elegant. How did they actually see if it worked for translation?
Well, they went straight for a big benchmark, the WMT14 English to French task. Standard competition.
And they trained it on a lot.
Oh, yeah. A massive amount for back then. 12 million sentence pairs. English and French.
Wow.
It's a ton. And for practical reasons, they had fixed vocabularies, like 160,000 English words, 80,000 French. Anything else just got tagged as unknown, UNK.
Okay. And to measure quality, they used BLEU scores. Got it?
Yep, BLEU, bilingual evaluation understudy. It's the standard way. Compares the machine translation to good human translations. Higher score, better translation.
Got it. So they train these LSTMs on millions of sentences, evaluate with BLEU. What happened? What were the scores?
Okay, so first big result. They used what's called an ensemble. 5 deep LSTMs trained separately, and they averaged their predictions.
Like getting 5 opinions and going with the consensus.
Exactly, and that ensemble, translating directly, got a BLEU score of 34.8.
Okay. Is 34.8 good? How does that compare?
That's the key question. You compare it to the state of the art at that time, which were these big, complex, phrase-based statistical machine translation systems, SMT.
Right, the non-neural approach, lots of statistics, phrase tables.
Very different beast. And the best SMT system on that same data scored 33.3.
Wait, so the LSTM ensemble, this purely neural thing, beats the established complicated SMP system?
By a significant margin. That was the shocker. First time a purely neural system had done that on a major, large-scale task, even with the fixed vocabulary limitation. Huge deal.
Wow, okay.
Yeah.
That alone is impressive. But you mentioned they did something else too, rescoring.
Yeah, that was their second approach. They took the existing SMT system, had it generate its top, say, 1,000 possible translations for a sentence, and then they used their trained LSTM model to basically pick the best one from that list. The LSTM rescored the SMT's candidates.
Kind of like using the neural net's judgment to improve the SMT output.
Exactly, and combining them like that, it pushed the BLEU score up even higher, to 36.5.
And how did that compare?
That was really, really close to the absolute best score reported on that WMT task at the time, which was 37.0. So it showed their model was powerful alone, and it could supercharge existing methods.
Okay, this is all making sense, but now, the weird part, the paper talks about this, like, counterintuitive trick they found.
Yes. This is probably the most famous takeaway. They stumbled upon something really unexpected. If they simply reversed the order of the words in the input sentences.
Just the input. The English.
Just the English input sentences, not the French output. Just flip the word order during training. That alone dramatically boosted performance.
Reverse the input. Why would... That sounds like it makes things harder. How much of a boost are we talking?
Get this. For just a single LSTM model, not even the ensemble, doing this reversal jumped the BLEU score from about 25.9 all the way to 30.6.
That's a massive jump. For just reversing words, what was their explanation? It seems so random.
Well, their hypothesis was about minimal time lag. Think about it. Normally, the first English word might correspond to a French word maybe midway through the output sentence, quite a long distance for the model to connect them during learning.
Right.
But if you reverse the English input, now, the first word the encoder sees is actually the last word of the original sentence, and that word might correspond to a word much earlier in the French output.
I think I see. So it sort of brings related words closer together in the sequence, the model processes, especially near the beginning.
That's the idea. It makes it easier for the learning algorithm for backpropagation to sort of figure out those initial connections between input and output words. It simplifies the optimization problem, makes learning more efficient somehow. A simple hack with a big impact.
That is fascinating, just changing the data order. Okay, another thing. Early sequence models often struggled with really long sentences, right? Did this LSTM approach have that problem?
That's another surprising finding. They specifically checked for that because, yeah, it was an issue for other models. But their LSTM, especially with the reverse source trick, it performed remarkably well, even on very long sentences. No big drop-off in quality. They showed graphs in the paper, pretty consistent BLEU scores across different lengths. That was another point showing how robust this was.
Wow. Okay, so it translates well, handles long sentences. Did they look into what the model was actually learning, like that fixed vector, the summary? Did it capture real meaning?
They did try to analyze that. They used PCA, principal component analysis. It's a way to visualize complex data.
Right, to see if sentences with similar meanings ended up close together in the vector space.
Exactly. And they found that, yeah, it seemed to work. The vectors did seem to capture meaning, similar sentences clustered. Interestingly, the vectors changed if you reordered words, so it cared about structure, but they were less sensitive to things like active versus passive voice. If the core meaning was the same, the vector representation was often quite similar, even if the grammar changed.
So it was learning something deeper than just word-for-word mapping. It got the gist.
It seemed to be capturing some higher-level semantic content, yeah.
Building this thing. 384 million parameters, you said. That sounds massive. Any quick notes on how they actually trained it?
Sure. Deep LSTM's 4 layers worked best. More layers helped. Standard training method, stochastic gradient descent. They did clever things like batching sentences of similar lengths together for efficiency.
Makes sense.
And used techniques like gradient clipping to keep the training stable. But yeah, it was computationally heavy. Took about 10 days on 8 GPUs back then.
Okay, so let's pull back. The big picture takeaway from this paper is?
I mean, it really showed that a relatively simple end-to-end neural approach, this sequence-to-sequence LSTM, could hit state-of-the-art on a really hard task like translation. It beat the complex established systems.
Even with some limitations, like the fixed vocabulary.
Right. And the key things that stood out were the power of that basic encoder-decoder structure, the surprising effectiveness of reversing the input source.
The magic trick.
The magic trick, yeah. And its unexpected ability to handle long sentences so well.
So the authors kind of concluded, didn't they, that this success meant the approach could work for lots of other sequence problems, provided, and this is the catch,
provided you have enough data. That was the key caveat. Lots and lots of training data.
Which leaves us, and you listening, with a thought. What other kinds of problems out there look like sequence-to-sequence tasks? Where else could taking one sequence, transforming it into another, using this kind of approach, maybe lead to similar breakthroughs if we just have the data, something to think about?